in addition to getting down all of these terms here, you definitely need this law. We covered it before, but it comes into play again today. And you need down this speed, 186,000 miles per second. What is that the speed of? Light. Of course, it depends on what light's going through, but that's the average speed of light. And this little wave, you might recognize a part of this. We call that a sine wave. We're going to look at that today when we talk about the electromagnetic spectrum. So get that down now as I take roll. Just hold on, Nikki. Okay. Okay, this is not where you talk. This is where you quietly copy that information down. Jeff?
Yes?
Hi.
Hi. Oh, hi, Mr. Myers.
Yeah, man. That's what I'm saying.
Sorry, I forgot.
You have a question, Nathan?
Isn't that the same law with matter?
Yep.
Okay, 'cause I know I heard that.
So today is a big concept day. I remember when I first learned this, I was like, man, I wish someone had told me this sooner. Everything kind of came together. All these little bits and pieces I learned about science all of a sudden started to make sense. And I realized how cool it was, how it affects so much of life as we know it. You know, we've talked about electricity. Electricity is. We've talked about magnetism, the property of matter where there is. And we know how they're related. We know electricity can, and magnetism can. And you saw that in a motor. You saw that in a generator. You saw that in an electromagnet, your fishing thing. But when we talk about the electromagnetic spectrum, we're taking it even further. We're looking at how this is going to affect things far beyond just electronic devices. And in the one video you watched, the guy said, life itself wouldn't exist without electromagnetism. So we have to look at some very basic things, starting with just energy. Before we get into our lecture, to let you finish copying this down, let's just review from yesterday's lab. I gave you a couple challenges. One was to light all 4 bulbs. Is it possible?
Yeah.
Well, the answer is yes and no. No, if you follow my rules exactly, which said by opening and closing switches, light all 4 bulbs at the same time. You can make those 3 light, or you can make those 2 light. What you might have discovered is by kind of sort of closing the switch a little bit, you could maybe make that other one light up a little bit. It's barely glowing if you look closely right now. And the reason for that is the switch isn't fully closed. It's kind of like a conductor, but not quite. It is resisting a lot of the flow. And by doing that, I'm making my own little detour. It's not going to let as many electrons go through, but it'll let some go through. You know, I may have 2 roads, and this one's a lot skinnier than this one. And you might think, well, all the electrons are going to go down the wider road. Well, it's not that simple. As you know, we can have a big, wide road that could be very crowded, and a little skinny road that might not be as crowded. And so what actually happens in reality is some of the electrons might go down the skinnier road. Because even though it is skinnier, it is the path of least resistance. I can hop on the freeway, and if there's been an accident on the freeway or every lane is full of traffic, I might move slowly. I could take this little side dirt road, and I might actually go a little bit faster in some circumstances. So some of the electrons will choose to take that little detour. The only reason I brought this one up is because some of you did figure out how to accomplish that. and it may have seemed to defy some of the rules I gave you about series and parallel circuits. It doesn't, right? What you need to remember is that the circuits we used here, all the light bulbs were identical. And when that's the case, you can predict exactly, will it be bright or dim? Will the electrons go this way or that way? In reality, all of our parts that we use in a circuit aren't identical. And we have additional parts that maybe let some of the electricity through. It's not an all or nothing. In those situations, then you get weird little things like you saw here when that switch was kind of closed. Okay? So my rules I gave you aren't wrong, they are correct. It just gets a bit more complicated when the parts become different than, these are all the same right now. The second challenge I gave you, that you guys were not successful on, I really thought you would be. Second period almost did solve this, but not quite. I said, using the materials from the previous day's lab and the knowledge about series and parallel circuits, burn out one of these light bulbs with the electricity from the batteries. Does anyone now know the solution? Still don't know. I said you kick yourself once you find it out. Yes?
You take the battery out of the green thing?
No. You didn't have to take the battery out of the holders. Yes?
Isn't it like, did you mean like box, like table?
I did. And I kept saying, in order to solve this, A, you have to use your knowledge from the lecture about series and parallel circuits. And B, you had to think outside the box. And I went over to the lab stations and I said, the box.
So,
Jeff.
So then, did you mean like putting more batteries together to blow it up?
You got it. Okay? It's funny because Americans, when they're given a challenge like that, they automatically assume it's a competition between them, their little group, their little station, their little box, and everyone else. I never said beat everyone else. I said your challenge, to all of you I said, your challenge is to burn out one of the light bulbs using electricity from the batteries. And you were so focused on beating the other groups, it didn't occur to you that if all of you as a class had solved this, I would have given extra credit to all of you. Okay? In fact, it didn't require the entire class, but it did require several groups. Probably 3 of you would have had to work together. What ends up happening, though, on a challenge like this is you throw out everything you've learned to that point and you're just racing to the finish. Can I beat the other groups? And you fail to remember some of the basic stuff. These are some solutions I've seen. I saw yesterday and I see in past years. You take your light bulb and you hook it up to the battery pack and it lights, okay? And it's fairly bright. And then you go, well, let's add another bulb. When you add another bulb in series, does it get brighter, dimmer, or stay the same? Dimmer. And you're like, oh, we're getting close to burning it out. It's getting dimmer. Are you getting closer? No. Is dimmer going to burn it out? It's got to be brighter, right? And then the group adds a third one. Eventually they add so many bulbs that it no longer lights up. And they're like, oh, we burned it out. No, you didn't, because if I can go back and I can hook it up again and it still works, it's not burned out. The goal is to make it brighter. And some people think, well, let's add more wires. Do wires produce electricity? No. So by adding more wires, you don't produce more electricity. Just like adding more roads doesn't produce more traffic. You got to have the cars to have more traffic. See what I'm saying? Well, you can add additional wires here, and you might be thinking, well, by having more wires, I have a better conductor. It lets more electrons travel to the wire. Well, your conductor is already plenty big enough to burn out this bulb. Your supply of electricity is not enough. You should have arrived at the solution. It's not until 11. Okay. You should have arrived at the solution that you needed more electricity. Second period did. And towards the end, some groups got together and they were at least heading in the right direction. They realized they needed more electricity. But then they forgot the second part that I told you. I said, apply what you learned from yesterday's lab and from today's lecture. And that was this business of series and parallel circuits. Okay, by the way, that website that I had down here on the bottom, I don't know if you guys wrote it down. This is the end of it. It's a good one to look at to review the concepts from today. We know that we can hook up light bulbs in series. And if I were to put another light bulb, right here, Another light bulb right there. Those two light bulbs are in series. And we know that this one's going to take its piece of the pie. It's going to use some electricity, and this one's going to take some of the electricity as well. The voltage goes down. I have 10 volts here. This is going to have 5, and this is going to have 5. Put another way, 2 bulbs in series, it means that this one's going to hurt that one, and this one's going to hurt that one. It's going to slow that flow. It's going to make it dimmer. The rule for series and parallel for batteries, now I've got batteries hooked up that way, is just the opposite. 2 light bulbs in series hurt each other, reduce the voltage. But 2 batteries in series, think about it this way. The plus is going to be attracted to the negative, okay? And the plus here is going to be attracted to the negative here. By having 2 batteries, I have even more positive charges and even more negative charges. So my flow is even stronger. If I wanted to increase the voltage, what you needed to do is hook up 2 batteries in series in this arrangement. Now you may not have called it that before yesterday or the day before, but you knew this. You know that when you take batteries and you put them in a flashlight, you stack them, right? If you put them in this arrangement, you increase the voltage. If this is 1.5 volts, now I have 3 plus 1.5 is 4.5. You increase the voltage. You can also hook batteries together in parallel. Let me show you. I'll demonstrate here. Here is 1 light bulb. Okay, I'm going to run it off of 1 battery. You can see how bright it is. Ooh. Okay. Now, get ready. You might have to shield your eyes. I'm going to do 2 batteries. See how much brighter that is? No. No? Well, here, let's just move up to, I don't know, 4. Here we go. Ooh, see how much brighter that is? No? Okay, oh my God, my eyes are killing me. I'm bleeding. Okay, now I'm going to move up to, let's just skip ahead to 8. 8 batteries in parallel. See how much brighter it is? It isn't brighter. And you may be saying, well, that's because the other batteries aren't doing anything. They are. Consider this. If this battery right here dies, it keeps running, right? The others can provide what it needs. If this battery dies, the others can provide. Okay? If I have 8 batteries hooked up like I just did here, that setup's going to last a good long time. A very long time. A lot more than 1 battery. But does it make it go brighter? No. For that, I need to hook them up in series. I need a volunteer to come help. Okay, Zach, come on up. So we can get it on camera. You can stand over on this side. I'll just start with 2. You predict how many is it going to take to burn it out?
4.
5.
Okay, here's 2. Now it's brighter, right? Because they're helping each other, higher voltage. Then I'll do 3. Brighter, more voltage. Grab another battery there, Zach. Put it on top. 4. Brighter. And 1 more. Brighter. 1 more.
It's like explode. That's
It's
crazy.
like Lincoln Logs.
Okay. Yeah. Good.
Ew.
Oh my goodness.
See it flash out like a flash bulb?
Oh.
Okay. Too much voltage. That's all right. It burned out. Just take my word for it. Okay? So what we did in the case, or what you should have done if you got together in groups and were working together, to get more voltage, you hook them up in series. It helps push them forward that much more. To hook up these battery packs in series, do you go red to red and black to black?
No.
No. You do what?
Red to black.
Red to black, and then the last 2 get hooked up to whatever you're hooking them up. Now you would have had to do that with 3 packs, not just 2. But you'd go red to black, red to black, red to black, and you end up with a red and a black on the ends. Those are the ones that go to the light bulb. You get more voltage. Second period got close, but what they were doing is they were hooking them up like this. Red to red, and black to black. And your assumption might be that's doing nothing. Well, it doesn't make it burn brighter, but it would last longer. this is the kind of arrangement you would want to do if you're jump starting a car. Okay? Here if we have 12 volts, that's what a car battery is. And let's say that 12-volt battery dies. It can't provide flow to your car. We'll just pretend the light bulb is your car. So you come up with the other car, the other battery, and you hook the red cable to the red and the black cable to the black on your battery. Do you see how that's then going to supply the flow to the car to start it? And this 12-volt battery will start the car. If I have two batteries hooked up like this, do I have 12 or 24 volts? 12. Okay? When they're in parallel, they don't increase the voltage. It just means that this can't supply the flow, this one can. It's like a backup, if you will. As opposed to if I did this, if this were 12 volts and this is 12 volts, how much would I have in the light bulb? 24. Yes? Nathan?
If you have like a 9-volt battery, like if you have two of them, can you hypothetically start a car?
No. You can't hypothetically start a car because a car may take as much as 550 amps.
Oh yeah.
That would not be capable of producing that flow any more than a little canteen this size is going to be capable of totally soaking you with water. You know what I'm saying? The smaller the battery, the less flow it can provide. Yes?
What if you actually put red to black, black to red in your car?
Accidentally, I can't ever imagine that happening. I can't ever imagine that I did that and totally fried my jumper cables. Because I would be really stupid to be a science teacher and to accidentally put red to black and black to red on a car. No.
That's shocked.
If you run flow, remember, things that run off of direct current, that's what we get from a battery. They don't like it when it goes the wrong way. And when you hook up things backwards, bad things happen. Parts get melted, get burnt. Yeah, I was lucky I didn't fry the electrical system on my car. Okay? All right. So that was yesterday. Now today, it's all about energy. We're going to start with looking at different forms of energy. Okay? We looked at how we have different forms of energy in this room. Can you name some? What energy is in this room right now?
Gravity.
Gravity. Okay, what else? Okay, alternating current. Some other obvious, remember on the very first week we covered different types of energy? Light is a form of energy.
Sound.
Sound. Keep it coming.
Heat.
Heat.
Smell.
No, smell is not a form of energy. Mechanical. Okay, we talked about all these different forms of energy. And most of these we can lump into one of two groups. We can refer to the energy as being potential or kinetic. Okay? Let me explain. Right now, as I stand here with my mug of water. Yeah, that's what it is, water. It's soda, actually. I am a soda junkie. I have potential energy. When I say energy, I'm talking about the ability to do work. I have the ability to do work. I have chemicals in my body that have given me the ability to run across the room and act like an idiot. Okay? But if I were to just suddenly die right now, I know, you guys are like, yeah, demonstrate, please. If I were to suddenly die right now, I would demonstrate that I did have potential energy. Okay? I couldn't run or do anything like that, but I would do work. What would I do if I suddenly died?
Drop the mug.
Would you spit out whatever's in your mouth, please? I would drop the mug and I would fall over. Both of those things happen because of what major force of the universe? Gravity. Okay? I am fighting that force right now. I'm standing upright. I'm fighting the force of gravity so I don't fall over. Okay? I have potential energy. If I did suddenly die and fell over, that energy would be transferred. It wouldn't just disappear. It would be converted into some other form of energy. I would use that energy to maybe crush my cup. I would use that energy to make the loud thump sound as I hit the ground. I've gone from the stored ability to do work to actually doing work. Potential energy is the stored ability to do work. Potential energy is the stored ability to do work. I went from actually Having energy, now I want to do something with it. Describe my potential energy now. Is it higher, lower, or the same?
Higher.
Higher. How did my potential energy increase?
Because now you have like more gravity.
The gravity stays the same, but I'm going to fall further, and I'm going to hurt myself even more. I'm going to make a louder thump when I hit the ground. I'm going to crush my cup even more when I hit the ground. Are you with me?
Yeah.
Where did the energy come from that I didn't have before that I do have now? Why do I have more potential energy now? Because I'm higher up. How did I get here? I stepped up. Did that take energy? Yes. So in order to get more energy in this body right now, I had to put something into it. The work, the energy doesn't just disappear. It goes to something. It took energy to get me up here. Now I have more potential energy. Okay? Once I take that energy from just being stored, right now I'm not doing any work. But when I put it into work, like falling, okay, then I'm doing something. That leads us to this next term right here. It helps a lot to know Greek and Latin roots. You understand pre and post, what those words mean, those prefixes mean. It helps you to figure out what a word is. If you know this first part, K-I-N-E, you know what it means. You might recognize another version of how it might be spelled, C-I-N-E, okay? Both of those things refer to, any ideas? I took a class in college called kinesiology, the study of human movement. This word you might see as part of a bigger word if you put your ma at the end.
Cinema?
Cinema. What's cinema, Patrick?
Movies?
Movies. Moving pictures. The pictures moving by, okay? So cine as in cinema and kina as in kinesiology, the study of human movement, both of these happen to mean movement. So when you see kinetic energy, you're thinking energy of movement, of motion. And this covers a lot of different forms we talked about. Kinetic energy, energy of motion. Kinetic energy, energy of motion. I had my potential energy, I was standing up here, kinetic energy as I was falling. Kinetic energy could be you running across the room. You have energy. It transfers, it turns into something else when you run into the wall and you do work. You leave a hole in the wall. You leave a hole in your head. You make a loud sound. We don't create or destroy the energy. All we do is change it from one kind to another. Moving wind, moving water, moving machines, mechanical energy are all examples of kinetic energy, energy of motion. Who's been to a hydroelectric plant, like a dam where they produce electricity? Okay, Hoover Dam?
Yeah.
Is that what it was? They talked about Grand Coulee Dam on one of the videos we watched. Well, the energy we could talk about in terms of potential and kinetic. Okay, again, kinetic energy is energy of motion. You got it? There has to be movement. The energy that we get from one of these dams can all be traced back to two things: the sun and gravity. Okay, let me explain. The sun's energy reaches the earth and causes heat. Water evaporates, clouds form, weather patterns form because of different temperatures. Clouds move around, they rain down on the mountains. Water lands on the mountaintop because of gravity, carrying it down. It runs downstream because of gravity. We stop it behind a dam. We keep it from moving. It wants to go this way. It has what kind of energy? Potential. It's not doing anything yet, it's just sitting behind the dam. When we let the water out, like you see in this picture, we're letting it go through pipes. It's going to turn a big wheel, a big turbine. Attached to the turbine is a generator with a coil of wire and a magnet. Those things spinning creates electricity. And we can trace all that back to the sun and gravity. Okay? Once that water is flowing through the pipes, we have what kind of energy? Kinetic energy. The water's flowing through the pipes, it's moving. When it's moving the turbine, it's kinetic. When that machine is doing work, it's still kinetic, but we call that kind of kinetic energy. Moving machine is mechanical, okay? So you can see now how all these things are related, hopefully. Let's jump into electromagnetic spectrum. You name some different forms of energy in this room. Did you include everything? Got everything on your list now? Sound, light, heat, chemical, all that. Anything else that is in this room? Any other forms of energy you didn't name? You guys happy? That was it? Yes?
What about weaker and stronger?
Okay. Oh yeah, those are definitely here. One of the four forces in the universe. Electromagnetism, gravity, the weak and strong force that hold atoms together, make atoms work properly. Okay? But what I'm getting at is that we often think, mistakenly, if we can't see it, taste it, touch it, feel it, hear it, it doesn't exist. Okay? And the truth is, we often think that if we can't experience it with our senses, it doesn't exist. Oh, there's nothing here because I don't feel it. And we know that there is something here. What is it? What's right here? Air. Okay? So we can't always rely on our senses. And what you might be surprised to realize is there's a whole bunch of other stuff with us right here in this room right now. There's some energy right here. You see it? Do you? Do you smell it? Can you taste it? There's energy right there, and there's some back there too. And I think I can detect some right over there. See, I can detect this energy because I have a special device. I have a radio back there. My radio lets me detect that there are radio waves right here in this room, zipping right through your body, and you don't even know that they're there. I can detect that there's X-rays in this room, gamma rays. But I need a device for that. Of all the energy that's in this room, you guys can only detect little bits and pieces. Now, you're a human. A dog might be able to detect energy forms that you can't detect. You can hear sounds, they can hear other sounds that you can't detect. A bumblebee can see light that we can't even see. Snake can as well, okay? We only are able to detect little bits and pieces of energy. The rest of it is around us all the time, and unless we have some device like a radio to detect it, we don't even know that it's there. And the big concept, the big thought for today has to do with this electromagnetic spectrum. And what we know is that energy comes in a whole bunch of different forms. And the kind that we're going to talk about today, they are basically the same thing. All we do is change one thing about it. I'll illustrate this here for you with Mr. Slinky, a fun and wonderful toy. Okay, so my Slinky now is going to represent the energy and how it flows through the universe. I want you to imagine right now, Matt, 8th grade. I want you to imagine right now that the universe is one big, giant, still pond. Way out there in the forest somewhere. The water's completely still. And when energy travels through the universe, much of it, not all of it, but the energy we're going to talk about today, travels in waves. And we refer to the wave as electromagnetism. It's like taking a little pebble and throwing it in the pond. Okay, and you get a little ripple. And that ripple will travel all the way to the other side of the pond. Okay? When I do this, I see that wave go all the way down to the other end. And that wave starts as a wave of energy, of electricity, excuse me. When electricity is flowing, what do you know that it creates? Magnetism. Whenever there's moving electricity, you're going to get some magnetism. So we get electricity, and at the same time that occurs, the electricity makes magnetism. You see that? The magnetism goes at a right angle to the electricity. So every ripple of electricity creates a ripple of magnetism. Some of this energy you can see. When I turn on a flashlight, boom, I send out a ripple of that energy, of electricity and magnetism. And it will travel and go on and on forever, unless it is absorbed by something else and turned into another form of energy. Okay? So every wave of electricity makes a wave of magnetism. And it's kind of fun to simulate this. You do it with your hands. Here's the electricity. Come on. Electricity. See, I knew that. And here's the magnetism. Like a snake. Electricity, a dolphin, magnetism, like a snake. And it's really, when I learned about this, I thought, this is super cool. Because the thing actually builds itself over and over and over again. What we're looking at here, this little simulator, shows you the flow of electricity in red and the magnetism in blue. Come up here. Here it goes. The flow of electricity in red and the magnetism in blue. Whenever I have moving electricity, I'm going to have moving magnetism. Whenever I have moving magnetism, it's going to make moving electricity. So each piece creates the next piece. And the thing recreates itself and goes on and on forever. One form of electromagnetism is light. You want to send a message to the aliens? Go out, dark night, take a flashlight, and do this. On, off. You just sent a wave. You put your little pebble, you threw it into the pond, you started that ripple. Even though you turned off the flashlight, that wave is still heading out into space. At what speed?
186,000 miles.
186,000 miles per second. Even though that's fast, since things are so far apart in space, it may take 10,000 years before that reaches some alien on another planet. He looks down and he goes, oh, Jeff's playing with the flashlight again tonight. And they get out their flashlight and they send the signal back to Jeff. 10,000 years later, it reaches Jeff and he goes, oh, yeah, they got my message. Okay? That ripple just keeps going on. Now, unless something intercepts it along the way and turns it into another form of energy, like when light turns into heat, you know, when light shines on an object and creates heat, it's changing it to another form of energy. It doesn't just go away. It doesn't just disappear. It's not created or destroyed, it's only changed. Yes?
So, like, how come when you shine a flashlight, like, in space, is it because your vision, you can't see it, like, go so far? Like, you can see your light and then just, like, see where it stops. Like,
See
when you
where it
shine
stops?
Yeah, when you shine it up.
What you have to remember is that in order for that light to really make it out into space and travel long distances, it has to be, it can't be blocked or absorbed or changed along the way. All the little particles in the air itself will absorb some of that energy and turn it into other things like heat. But if we didn't have those things between you and what you're aiming at, that energy would go on and on forever. And that's how we're able to send radio waves off into space. That's how we're able to see light from stars and planets. Okay? Stars that are billions of miles away. That light that's reaching us is old light. It took a long time to get here. In fact, we can look in our night sky and see things that are no longer there. You know what I'm saying? The star was giving off its light. Boom, boom. It takes a while to reach you. Is that really that painful? It takes a while to reach you. And meanwhile, boom, the star dies. The light is still coming towards you. It takes a while before it's no longer there. Yes?
If the sun went out, you wouldn't know for like 20 minutes.
Exactly. Okay, here's what I need you to write down for this one. I would do this on a whole new page because there's lots of little bits of information. First of all, so I turn my page sideways. Along the top, I would put radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. These are the different forms of electromagnetism. Different flavors, if you will, of electromagnetic energy. Radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. What I showed you there with the slinky, the positive and negative flow of electricity, the peaks and the valleys, creates magnetism that goes like a snake. The energy that we pick up on a radio is the same basic type of energy that you can see as light. The only difference between the light and the radio waves is the length of each of those waves and how quickly I move that snake back and forth. Got all those written down? Below that, what you might want to draw, you don't need these numbers. Don't worry about the numbers. You might want to draw a wave, like the sine wave we drew before, but it keeps repeating itself. Makes itself over and over again. And show that how that, as we move from left to right, that wave gets shorter and shorter. The length of the wave, the length of one wave gets shorter and shorter and shorter as we go to the right. We could describe that a different way. We could say that if I measure this amount of time, I only get one wave. Down here, I measure that amount of time, I might get 5 waves. We say the waves are happening more frequently. How many occur in a given amount of time is referred to as the frequency. They're happening more frequently. I'll give you the definition for wavelength and frequency again here at the end. Above radio here on the left, you might write AM. On the right of it, you might write FM/TV. AM, FM/TV. Above infrared on the left, you might write heat. On the right, you might write IR, light. What does IR stand for? Infrared. IR, light. Here. Below your little wave, I have lengths or sizes that you can compare how big that wave is. An AM radio wave is going to do one of these, positive and negative flow, and that might take 400 meters for it to do one of those, or 100 meters, or 300 feet. It all depends on which frequency, like a radio station, which frequency we're talking about. But those waves are very long as a building. When we move from radio waves to microwaves, the waves are much, much smaller. Okay? In between we have FM and TV. Those waves, they could be a meter long. So they're going to do one positive and negative flow in about that much space. Again, you're not going to see this because it's going through the air. It's electricity and magnetism. You can't detect this particular energy. You got to have a radio for that. Nathan?
How do people know how big they are when they can't see it?
There's a lot of different technical ways of measuring it indirectly. Okay? The next one, infrared energy. Right in here, then, we're no longer going to see it. We're going to feel it as heat. I'll talk about that in a second here. Those waves are much, much smaller. Microwaves are about a millimeter. It says honeybee. Well, it depends on the microwaves you're talking about. They can be as small as a millimeter to do one peak and one valve. Much, much shorter, smaller waves. When we start getting up to light, the wave length, the length of one wave of, let's say, orange or yellow, is so small that we're talking about the size of little microscopic forms of life you might find in water called protozoa. Okay? Little teeny tiny microscopic length of the wave. You might say, well, it's getting really small, so it's not as powerful. The truth is you take this and you scrunch it together, you've got a lot more energy down here than here. You can do a lot more damage down here. We get down to molecule size when we're talking about ultraviolet light, which you can't see. Beyond that, X-rays are the size of atoms. Those little waves do that in the space of an atom. And a gamma ray is so small it's like the center of an atom, the atomic nucleus. You don't need to write this down, but you should write this down. Roy G. Biv. You know what that is?
It's red, orange, yellow, green, blue, indigo, violet.
Okay. So I want you to take away a little bit of information about each of these in the time we have left. So let's back up to radio waves. AM versus FM. Which one has a longer wave? AM. These are always longer here. When we go this way, they get shorter. Likewise, if you're trying to pick up an AM radio station, the antenna is going to be longer. If you hooked up antennas to the back of maybe your stereo, you might have seen that for AM, you have this spool that has a bunch of wire wrapped around it. Anyone know what I'm talking about? Okay, a couple of you do. That's a very long wire to pick up a long wave. As opposed to FM, you have usually a wire that's about that long, close to the length of the wave. Shorter the antenna, the shorter the wave is going to be. You're trying to pick up a smaller wave. We'll talk more about that in the coming days. The antenna on a cell phone. Cell phones work using microwave energy. Now, most of the antennas are built inside now, but some of you have a little thing that sticks out. Usually the antenna is only about that long. Well, we have a much shorter wave here we're trying to pick up. Microwave ovens were once called radar ranges. First microwave oven I had was called a radar range. And that's because the energy that they use for radar dishes when they're trying to pick up planes flying over is microwave energy. And the first microwave, there were some airmen that were using a radar dish way back when in like the 40s or 50s. And it was a cold day, and they went over to the dish, and they realized the air around that dish was warm. They warmed their hands over it. And somebody looked at that and went, they're heating up stuff with the radio waves. And the first microwave oven basically took a radar emitter, a radar transmitter, put it in a metal box, and aimed it at your food. It would cause the water inside your food to start vibrating. When that water vibrates, it creates heat. The water heats up, the food cooks. What do you think was one of the first things they cooked in a microwave oven? Popcorn. Popcorn works great because all you have to do is heat up a little bit of water and oil inside the kernel, and it expands and the thing explodes and turns inside out. But we are actually cooking with microwave energy. Your cell phone uses microwave energy, but not as much. Therefore, it's hopefully not going to cook your brain when you hold it next to your head. Although there was some concern about that, and there have been some studies done that maybe you shouldn't hold your phone close to your head. The farther away you get it, the less radiation you get, because it's giving off microwave energy, just like your microwave oven. Okay? The difference is this is much more powerful than this. So if you're going to have an hour-long phone conversation, use your little earpiece or something. Get it away from your head so you don't get brain cancer. I'm not saying it's going to happen, but there were some concerns about that because it does give off microwave energy. So this we can't detect at all without some sort of device. Okay? When we get up to infrared energy, we get to energy that we can't see yet, but we can feel as heat. Now, I'm not saying that all heat is infrared energy. Okay? When you put your hand on a hot stove, it's not infrared energy that makes your hand hot. But when you look at the stove and you see it glowing red, some of that red you're seeing, of course, is light. And some of the energy that's coming off of the stove you can't see. It's in a range that you can't see, but you can feel. You can feel the waves of heat coming your way. Okay? You can feel it as it heats the air. The energy that reaches the earth, it helps heat it, is in the form of infrared energy. It heats up the ground, it heats up the air, and makes the earth warm and toasty. Okay? That's energy you can feel, but you can't see. As we make the wave a little bit shorter, now we're into what we call infrared light energy. Your infrared remote gives off light. Maybe you try to see that. Ever try to look at that in the dark? Hold a button down and look at your remote in the dark?
Yeah.
Try it. Sit in the dark room for like 5 minutes, then hold the remote close to your eye and press the button down, and you may see a little dull red flicker. You can see some visible light, but typically your eye cannot pick up that length of wave. The wave is too long for your eyeball to see. When the wave gets shorter, then we get up to this area where we can start to see it. This specially treated paper will show me that flicker. It's turning it into a wavelength that your eye can see. You see that? Okay? So infrared light's pretty cool because it's like invisible light. If I have a device that can turn it into visible light like this, like infrared goggles you see in the movies, okay? You know when you see those images and everything's all green? What they're doing is they're using a giant version of a remote control. It's giving off infrared light. It's like a flashlight, but you can't see it. And I'm shining this invisible light on you. It's bouncing off and coming back to my goggles, and my goggles turn it into something that I can see. Firemen use it to rescue people from burning buildings. There's a hand up? Yes.
Yeah, like, what about, you know, like, video games, they have this, like, shooting video games, they have infrared goggles where you can see, like, heat of people
Yeah.
at nighttime.
And you can see because those two wavelengths are very close. We can tune our infrared goggles to pick up the heat that they give off, or better still, we have our own infrared flashlight. Some security cameras have lights that shine on you, and you walk up to it, you don't see a thing. It's infrared lights, like having a whole bunch of remote controls all shining on you. That infrared light bounces off of you, goes back to the camera, and the camera turns it into visible light. Yes?
So if you were to walk up to that camera with a suit made out of that paper on, you'd be able to see the light and be all lit up?
Yep. Yeah. All right. Visible light. At the very end of our visible light is this dull, dark red. Makes sense now? That's what we could barely see if you look at a remote in a dark, dark room. You might see a little bit of the dull red color. Beyond that, the rest is invisible to you. You can't see infrared. It goes from a dull red to a brighter red to an orange, yellow, green, blue, indigo, and violet. You should know what each of the letters stand for. You might want to write below it. ED. You know, RED. Orange, yellow, green, blue, indigo, violet. Why is the order important? Because we know that red light has less energy and is cooler than blue or violet light. And this knowledge is so important in so many areas of science. If you're an astronomer and you're looking up at stars and you want to know how old or how hot the star is, well, nobody ever flew to the sun and stuck a thermometer in to see how hot it was, or to all these other stars. We look at the color of light given off. And we know that if it gives off blue light versus our star, which gives off more yellow-orange light, which one's hotter? The blue one. Now you may say, well, I want the blue one then. It's better than this one. Well, this one's burning slow, and it will give us the right amount of heat for light to continue to exist. Depending on what you're burning, you can tell how hot it is. The brighter the color, the more towards violet it is, the greater the heat. Magnesium, when it burns, you can burn metal, you can melt it and you can burn it. When magnesium burns, it burns very bright. Do not look directly at the flame. Okay? That brightness is because we have more energy we're getting out. So you can look at the color of a star and tell how hot it's burning, and maybe even infer, guess, how long it's going to last before it burns up. Yes?
So have they found a star that says violet?
Yes.
So like
Okay.
mega hot?
Yeah. Ultraviolet is beyond what you can see. After we get violet, it starts to get dark again and you can't see it, like a black light. Okay? A black light gives off some visible violet colors, but it also gives off light that's in a range you can't detect. The waves are so close together you can't see it. The energy from the sun that keeps our, it gives us a suntan or sunburn or skin cancer is ultraviolet. Please don't pack up while I'm talking. We'll just stay after. If you sit inside your house behind a pane of glass, most of that light won't make it through, and you won't get a suntan. Okay? People mistakenly think that if it's a cloudy day and they lay out by the pool, they won't get tanned or burned. Ultraviolet light you can't see. It's not just the light you see, it's the light you don't see that gives you a tan. X-ray, those waves are so close together they're the size of an atom. And they're going to do some serious damage to you. You can damage tissues. if you expose them to too much X-rays. That's why they wear the big lead vest when they give you X-rays. Gamma rays, we're protected by a field around the Earth that keeps those rays that come from the sun from killing you. They're so powerful and so tiny. There's a lot of energy packed into a small space. Okay? This is just that same thing shown in a different way, giving you the sizes. But we're only able to detect a tiny little bit of visible light. The rest we need a device for. What is the frequency for each of these and the wavelength? If you didn't get those definitions as I was talking about it, watch the podcast. I'll have that last part on there. So once again, you can see the main idea here is the only difference between radio waves, AM, FM, microwaves, infrared, X-rays, gamma rays, visible light, is simply the length of the wave. If we look at one valley and one peak, one valley and one peak, we can see how those valleys and peaks get closer and closer together as we go from radio waves to X-rays. There's more energy in a smaller space of time. More peaks occur in a smaller space of time. We can talk about these peaks and valleys using words like frequency and wavelength. We talked about frequency a little bit already when we used the word cycle. A cycle is one positive and negative flow of electricity. Of course, we get a flow of magnetism with that as well. If we have one cycle occurring in 1 second of time, that would be referred to as 1 hertz. The number of cycles per second are referred to as hertz. How many of the peaks and valleys occur in 1 second? We get 1 sine wave, 1 cycle every second. It's 1 hertz. They often refer to this as the frequency of the energy. You know this because you know about the frequency of radio stations. On one end, we may have 1,490,000 hertz cycles a second. That would be an AM radio station. As we move towards FM, the number of cycles that occur every second will increase, and you might have 96.1 million cycles a second. Million versus 1,000. There's going to be a lot more of these in a certain amount of space. So as we go from AM to FM radio, the cycles each second increase. When you check up a radio station, that number is the number of cycles a second, the hertz. As we move down to the opposite end of the electromagnetic spectrum, there's a lot more energy, a lot more peaks and valleys in any given time of space. And here we can see in 1 second, there's more than 1 cycle. We can count. 1 is here, 2, 3, 4, and 5. There are 5 complete cycles in this 1 second time period. 5 cycles every second is referred to as 5 hertz. So in example A, we have 1 hertz. In example B, we have 5 hertz. We would say the cycles occur more frequently. The cycles occur more frequently. Those happen more often. Or we would just simply say this is a higher frequency. Based on what you have seen here, then, you can make some conclusions about wavelength and frequency. As the length of our wave gets shorter and shorter and shorter, so the wavelength decreases, what's going to happen to the frequency? Well, here you can see 5 occurred in the same space that 1 occurred here. So the frequency increases. And here are all the definitions one more time for you. Potential energy is defined as the stored ability to do work. Kinetic energy is any energy of motion. Moving air, moving water, a moving person, all have kinetic energy. We might refer to it as wind if it's moving air, or mechanical energy if it's a moving machine or person. but they all fall under this grouping of kinetic energy. Electromagnetic spectrum is energy ranging from radio to gamma rays that grows stronger as the wavelength decreases. The frequency will also increase. So from radio to gamma rays, the energy gets more powerful, more intense, more peaks and valleys in any given period of time, higher frequency, and a shorter wavelength. Frequency is the number of cycles occurring in a given period of time. If we're interested in a period of time of 1 second, then we would refer to that as hertz, the number of cycles a second. If we're just talking in general terms, are we getting a lot every minute, every hour, every second, we say frequency. So the two words are definitely related. Wavelength, the distance the energy travels in one positive and one negative flow, or a cycle. The peak-to-peak distance. Let me explain. I can measure the frequency by measuring the distance between peaks. Or I could choose to measure the distance between the valleys. These two measurements would be the same.